Now we're going to look at second math, what I call as math 2, as the title suggests. And again, if you haven't done math 1, go ahead and do it. And if you haven't seen these equations or how to derive them, go ahead and do them. But just as a reminder, we are in this zone where we are looking at the monod kinetics for the CSTR, and these all apply. Mu equals to D applies, S equals to dKs divided by mu max minus D applies, and this equation applies. And also, if you need a D optimum, this is the equation to have in mind. Okay, so let's go to our math number 2, as I call it. Yeah. So here, so before getting into the nitty-gritties of this is a series CSTR type math. But even if you don't go for the CSTR, like you can even just solve for one CSTR and be done with it. You see how. Let's just read it. Monod kinetics are considered in a CSTR with an organism growing with an initial substrate concentration of 50 gram per liter and kinetic parameters of Ks given, mu max given. What would be the maximum dilution rate? That means they are asking for the D for a 90% yield of biomass with the maximum rate. And in the second part, we have if the same dilution is used, what would be the number of CSTR in series? So let's do it part by part. Let's do part A first. So in part A, what are they asking? They're asking for what would be the maximum dilution rate, meaning the optimum dilution rate. For that, we have a very convenient formula. So we just put them in. And let's see if we have all the parameters we need. Ks. Ks is 2. Si. What is Si? Si is 50. 50. Mu max is, yield is 0.9, but we don't really need it. But yeah, it's good to know. And once we put that all in, we should get our D optimum. Don't be convinced without doing it. Go ahead and do it and convince yourself that this is the correct answer. Sometimes I do get wrong answers on the slides. So if you have any doubts or issues, definitely let me know. Okay, so what did we do here? We got the D optimum for this one CSTR. So that should have been the end of it. We got the D optimum done. They have a second part though. If the same dilution is used, what would be the number of CSTR in series? Well, you didn't even talk about the series. Why are you talking about the series now? So that question can be answered. Like we know the D optimum. So before we get into the series, let's just look at what we get as the S out. Okay, let's look at each of these. Let's call this CSTR1. Okay, and like for a minute, just imagine that we don't even know about CSTR2 yet. Let's just look at this. Let's focus on this one. You basically have an SI, or you can even call it an S0. The out will be then S1. S1. Then you have Fi, which is basically equal to F out, Fi or F0, and F0. And you also have some biomass, right? Let's call it X0. And you have X1. Why instead of I am making it not is simply because this can be considered as CSTR I, where everything getting inside is I minus 1 and everything coming out is I. Same for this one. So let's call this CSTR I. In this case it will be 2. So everything coming out of here, if this is S1, now you're putting in S1. So that is your basic series, CSTR in series. But why would you go ahead and do that? For that, let's look at the actual xi that we are getting. Okay, just bear with me for a minute. We can actually figure out si. Yeah. So this was your CSTR1. You have your S not getting in, X not getting in. Coming out is S1, X1. So they are telling, let's consider, let's take the solve for the substrate. So let's see what we get as the S1. S1 is, we know from our derivations, is simply dks mu max minus d. Still our 90% yield is not getting used. We got a d from our part A, we put that in, D is 0.402 because they have said the same dilution is used. Ks we know, mu max we know, and D we know. So how much is our S1? Convince yourself that this is what you're getting. And also convince yourself that the yield is not still coming into play here. So that's your S1. So S1 is coming out to be something like 8.2. Here is the catch. We are at optimum. Like this is the highest D we can possibly use for CSTR1. But look how much of substrate is still left. If you have enough biomass even, and if you have enough X1 even, you could actually go for another CSTR to get some more product. So that's the idea of the CSTR series. So let's just take all this and then put it in another CSTR, call it CSTR2, where this is your feed, this is your new X inside, and you get an X2, S2, and so on and so forth. All of this should then follow, that they should get the same sort of effect, except for one. I'll ask you which one that is not going to be the same. Same dilution is used, so D is the same. That's not a problem. D is the same here. Something here, some kinetic parameter here cannot be used here. Think about it. You will get the answer in a few seconds. But yeah, think about it. Which is the kinetic parameter that you can use here, but not necessarily it is the same here. Okay. So next, let's think about, we got the S1. What about X1? How much is the X1 and where can we get that from? What is the X that comes out of this CSTR1? Do we know X0? No, not necessarily. But what we do know is, what is our, oh yes, we do know X0. Because normally X0 is 0. So we can actually figure out our X1. And we have done that. We have actually some formula. But even if you don't know the formula, you can just think of y x is as x1 minus x0 by s1 minus si or s0, however you like it. They have used s out minus s in, however it fits you. So just rearranging this, and this is 0.9 and this is 0. We don't know x1. S out we got as 8.2. And S in we got, sorry, out, yeah, 50. So rearranging all that, this is what you should be getting, and convince yourself that this is the X1 that you're getting. Okay. So convince yourself. So this is the X1 that I got. Okay, you convince yourself. So let's go to the physicalities of this. Coming back to our diagram, this is our 37.6. Just putting the formula and everything. So look at these numbers. Gram per liter. So much of X1 you have and so much of S1 you have. If you just took this bunch and just put it in your new CSTR, you would just get so much more product. So just to make this whole thing more efficient, they are saying that we can do CSTRs in series. But how far should we go? The answer to that is, there is really no optimum, like an optimum number, optimum type, or HTU, NTU sort of situation. What you do is you just go manually and you figure out what is your S2 here, and if you see that this is still so big, then you go for another one, and so on and so forth. Okay, so it's like a sort of, not a trial and error, but sort of number iterations rather. Okay, so let's see what else we are supposed to do. How do we actually figure out what is the S2? Okay, or can we just plug in the numbers and find out S2? Yes, we can, but we're going to go in a certain uh, general equation, let's just say. So general equation, if you think for any CSTR in series, it is Fsi minus 1 minus Si is equal to V because your field is the same and same dilutions used. That's why you can use all the same S's and V's, F's and V's, and V multiplied by rate of substrate consumption. Now, rate of substrate consumption from previous knowledge we know is what? Y-axis is basically Si minus S naught, Xi minus X naught. So, rate of biomass growth on top divided by Y. So, Si minus S naught is basically Xi minus X naught by Y-axis. But for monods and everything, we basically know that this is mu X. Okay, whatever is your X right now, you just multiply by that. So, that's what we did here. D S feed minus S, or as I like to call it, D Si minus 1 Si minus 1 minus Si is equal to mu X divided by Y-axis. Okay, so that's your basic thing. And furthermore, your mu X, this is the catch. The second tank is not operated at mu max. Remember I said I'll tell you in a few seconds which is the one that is not used. This is the one that is not used. You can't just write mu max and try to get the optimum out of all this. If it was operating at mu max, you would just put in all this and just get the SI. Okay, because you know it's the optimum in mu max. The catch is that you cannot use this because it was at the optimum and you would have just figured out S2. So you have to use the basic equations for mu, which is this one. And this is like, if it's for CSTR2, this is going to be, or if you like it, the general one, it's like this. So KS is fine, mu max is correct, but your mu, you cannot just use this as mu max. In your original derivation of this thing, you had assumed that at the optimum mu max is operating. But now that you have a CSTR2, you cannot assume that because you have lower mass, biomass, and you have some less amount of substrates. You just have to use a mu. You cannot just use mu max. So that is the catch. After that, the maths is pretty easy once you know the why we are getting here. So in the spirit of I and I minus 1, this is D S I minus 1 minus Si minus mu max, because it's mu max Si and Xi, because this is going to be the one that is coming out, not the I minus 1, divided by Y. This is Ks plus Si, so it's Ks plus Si. And now if you put it in like 1 or 2, both of it will work. I am putting it in the CSTR2, so it becomes D S1 minus S2 minus mu max S2 X2 Y S2 Ks, S2 plus Ks. Okay. Remember I said if I knew that this is operating at mu max, I would just put it in the D optimum and I would just figure out from this formula the Si or the S2. Here we don't know the S2 because it is in a quadratic sort of an equation. So my whole point was that if I just knew S2 and I would be like, yeah, it's low enough that we can stop, then we could have just, if we have a CSTR1 and a CSTR2, and in CSTR2 if the substrate is low enough, we could have just stopped. So that's my question. Is S2 low enough that we can stop? And then we would say the number of CSTR is wherever we are at. In this case, it will be 2. If it's not, then go for this whole thing again. The D Si minus. So you will go for D S2 minus S3 and check out what is S3. And if that is not low enough, go for S4. So that is where this thing gets solved. The physicality seems a little bit complicated, but it's not. Think carefully about it. And just the basic of this is if Si or the S out of whatever CSTR you have is low enough, then you stop. Okay. And now let's go for the math. Let that sink in a bit while I erase this. Okay. So now what? I'm keeping on saying let's figure out S2, let's figure out S2. If we know S2 and if it's low enough, we can stop. So let's see if we know all this. Do we know D? Yes. Do we know S1? Yes, we do. Because we've done the CSTR balance, a CSTR1 balance. Do we know mu max? Yes. Do we know S2? No. Do we know X2? Do we? We know X1. Do we know X2? No. But we do know that X2 is simply a function of S1 and S2. So put that in there. Okay. So instead of X2, we have just written, sorry, instead of X2, we have written this part, y S1 minus S2. So let's see again. Do we know D? Yes. Do we know S1? Yes. Do we know S2? No. Do we know mu max? Yes. Do we know S2? No. Do we know X1? Yes. Do we know Y? Yes. Do we know S1? Yes. Do we know S2? No. Do we know Y? Yes. Do we know S2? No. And do we know KS? Yes. So you have basically an equation, a single equation where you don't know S2. So can we solve it? Let's see. Let's simplify this a little bit more, and you do this with me as well. Don't just sit there, copy this whole thing. So, and if I just simplify this like this, S1 minus S2 y S2 plus KS is equal to mu max S2 bracket x1 plus y S1 minus S2. Okay, makes sense? Let's simplify that further. This is just what I did. So if you simplify all this, you're going to get something like dy s1 s2 da, 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 minus dy s2 square and so on and so forth. And hint hint, this has only s2 square numbers and s1 s2 square s2 square and constant. I'm trying to say this will give you a quadratic equation in terms of S2. Because all of these you know. S1 you know, Y you know, X1 you know, S2. These are all constants. And you're getting a quadratic equation in terms of S2. Okay. So that solves our problem. We need to figure out what is S2. We have a quadratic equation. Go ahead and match this with mine. I'm going to leave this up to you because it's a video lecture after all. And yeah, so match these with mine. If your A matches with my A, B matches with my B, there is plus minus issues all over, but at least it's not a dy ds thing. It's just s square, s squared. So yeah, this is my quadratic equation. Solve this, see if you get this. And now let's check it out. Oh, S2 is 0.27. You had a whole 50 gram per liter in the beginning, and then you had like S1 as something like 8. Now S2 is coming at to be 0.27. Seems reasonable. So that's why we can stop. So we can actually stop at S2. If this wasn't low enough, if S2 was like 5 or 6 or something, then you would have to do this whole thing again. Now that you know S2, take that S2 and put it as S3. So your new equation will be dy S2 minus S3, S3 plus Ks is equal to mu max S3 x1 plus y S2 minus S3, where you have the same thing, same equation, just in this case you know the S2 now and you don't know S3. Okay, so it's like an iterative process where you stop when this is low enough.